Okay, Math 170, are you ready for implicit differentiation? I'm just imagining cheers in the background. It sounds really complicated, but if you remember that differentiation is just the process of you taking a derivative. And so we just have to define what it means, what implicit means in terms of math. So I'm going to kind of start off with an example where we can play with, and then we're going to discover a different way to approach it. Let's see if we can do that. So the first thing I want to ask for, what if they asked us to find the derivative of y with respect to x? So what if they want this from us given this function, x squared plus 4y squared equals 5? So remember, if you're trying to find the derivative of y with respect to x, the first thing you probably would look at is, in terms of all your other functions you've been playing with in the previous sections, I think you first have to solve for y. So let's play a little algebra. If I'm going to solve for y, I'll take the 4y squared. I'm going to move the x squared to the other side. So that would be 5 minus x squared. And then if we're going to solve for y, we divide everyone by 4. Let's isolate the y squared first. So we have 5 minus x squared over 4. And if we want to solve for y, that's a y squared. So what I'm trying to make sure I'm taking care of is, so you have to undo a square. I'm going to have to take the square root of both sides. So that would leave me with y equals, and remember one of those tricks, if we're taking the square root of both sides, we end up having to deal with the plus case, the minus case. And if I want to make this a little bit prettier, well, I'll let you discover this. If we take the square root of 4, we know we get a 2. And then if we take the square root of 5 minus x squared, well, we just get the square root of 5 minus x squared. There's no simplifying when there's a difference in your radicand. And so at this point, when we're looking at it, if it's solved for y, this is what we call explicit form. So you can kind of think about explicit form as the functions you know and love, anything that's solved for y. But I also want to point out that when you are in explicit form, your y is a function of x. Your y is rewritten in terms of x. So that's going to be important in this section. And by the way, I did say explicit, not implicit yet. So it is solved for y at this stage. Maybe if we want to try to find the derivative, I notice whenever I see a radical in the situation, it might be more beneficial if we rewrite it. So that would be my idea. Before I'm able to take the derivative, maybe take a little time to rewrite. We still have, let's see, what can I do? I see a denominator of 2. I don't want to, I'm going to try not to use the quotient rule if I can. And it looks like 2 is a constant. So let's play with this way. Let's look at it as plus or minus 1/2 multiplied by the radical. And this is where the rewriting comes from. Instead of using the square root, I'm going to use power of 1/2. And so that's the 5 minus x squared part. So that's going to be a little more friendly to try to take the derivative of. So if I want to take the derivative of y with respect to x, I'll just use the notation that they're interested in. We're keeping the plus or minus in our situation. Let's see if we can move it over just so that you can see where I'm going from. I guess either way. I'll do it this way. dy dx equals. I always like to try to write vertically. It kind of makes the numbers fall into place, and then my eyes don't skip over anything that might be important, like that plus or minus sign. So I'm just going to carry that down. That's really a factor of our problem. And whenever we're taking the derivative of a power function, if you remember, we take the exponent, we move it around in front in some manner. It gets multiplied by whatever factor was already there. Then we still have this 5 minus x squared part going on. We have to subtract off 1. So if we say 1/2 minus 1, that is -1/2. Now here's something coming back from 2.5. Aren't you excited to apply this new section? We're looking at the fact when you took this derivative, we had the case where the inside was more complicated than just a function of x. So we have to invoke the chain rule to attach on this link. So we have to take the derivative of the inside. Well, it's a difference of two expressions, two different functions. Derivative of a constant is 0. Don't have to worry about the 5. But derivative of -x squared, that would be -2 times x. So we want to be careful there. Now here, we could clean up the algebra just a little bit. Still got the plus or minus. 1/2 times 1/2 is 4. But we also see that we're multiplying by 2x or -2x. So one of those 2's can divide out. Your choice, which one. I also have an extra negative sign. But whenever you say plus or minus a negative, all it does is switch the direction of the plus or minus symbol. But then we always imply that it doesn't matter if one of them's plus or one of them's minus. It's still the same thing. So we don't have to worry about that extra negative sign. So I should be getting, if I can rewrite this, I do have 5 minus x squared to the 1/2 times an x over 2. So you may be seeing it like this. Let's see if I can make it a little prettier for you. We have an x in the numerator. And notice there's a 2 in the denominator. If we were to take this negative exponent factor, we can float that back down to the denominator by changing its power. And if you want to play around, if you have a power of 1/2, that's really just a radical. So I can then convert everything. This is plus or minus x over 2 times the square root of 5 minus x squared. And this, my friends, is the derivative of y as a function of x. So I'll circle it or box it and just kind of restate in English what we just found. We found the derivative as a function of x. And we found this from the explicit form. So that's one way to do the problem. And I believe if it doesn't specify how to find, how they want you to find the derivative, then you have that option. So you can recycle some of the stuff you know from the previous sections. Just got to be really careful with the bookkeeping, those negative signs and such. But we have another technique. It could help us, it kind of saves a little bit of time, and when the functions or the expressions, I shouldn't say expressions, the equations become more complicated, this is going to be the key to going to take the derivative. So if we already know from explicit form that y is a function of x. Okay, so just kind of think about it this way. So now, if we already think about so if we're already thinking about y is some function of x, because clearly it is. When we're going through this, when we solve for y, it is in terms of x. So that's where we're having this function notation. That's why we kind of went over functions so heavily in chapter 1. What happens is you could look at this expression. So we can look at, let me write this over again. I keep saying expression, but it is technically an equation. Is that an equation of an ellipse or a circle? I think more so ellipse. I don't think I'm seeing the same thing. But we're going to look at this way. X squared plus 4y squared equals 5. That's the same example we copied over again. But as long as you understand, whenever you see a y, it's a function of x, you can kind of play with taking the derivative of both sides with respect to x. So how I would denote this, and so I'll kind of think derivative with respect to x, I'm taking that of both sides. So I'll rewrite it. Kind of like equation solving. What you do to one side, you do to the other. Derivative is kind of an operation, so we'll go with it. So I have x squared plus 4y squared. Because eventually I'm looking for the derivative of y with respect to x. So if I do this, kind of keeping in mind this y is a function of x, we could kind of say, okay, if we have the derivative of a sum, that means we can take the derivative of each individual term. So if we kind of write this out, derivative of x squared with respect to x is 2x. There's a plus sign from the original equation. Now, derivative of 4y squared with respect to x, we have to keep in mind, one more time, that y is a function of x. So the best way I can describe this is you take the derivative how you think you would take the derivative. So derivative of 4y squared would be 8y. But the issue is y is a function of x. So y is not this nice single variable. So you would have to apply the chain rule to the y. And if we don't really know what y is, but we are talking about the derivative, you would attach a dy dx. It's kind of a good rule of thumb. And I'll kind of talk about this on the side before I proceed, but let me just finish the right-hand side. If I were to take the derivative of 5 with respect to x, then right away, derivative of a constant is always 0. So just a little note, this is what we're thinking about. It's called implicit differentiation. So I'll write kind of a little bit of a little, I don't know if it's a caution, but something to take notice of. Implicit differentiation, if we are taking the derivative with respect to x and we see y's. Okay, so implicit differentiation. I got to make sure I spell that right. A little note for yourself. If taking the derivative with respect to x and you see y's, the key is to always remember that y is a function of x. So it's not just a nice single x. This is where we have to apply the chain rule. And how we do this, just so I can take that little piece off to the side so you can really inspect what's happening. Derivative with respect to x of the 4y squared. Remember, we took the derivative of the outside. It's 4 times something square. So the derivative of the outside is 8y. I'll abbreviate deriv of outside. And we have to apply the chain rule. So this is where we attach on the derivative of y with respect to x. That's the derivative of the inside. I mean, the issue is we really don't know what y is, but we do know it has a bunch of x's in it. So that's how we explain this derivative. So this is where we're getting this dy dx notation. And rule of thumb, basically, if you always want to pay attention to, like, what are you taking the derivative with respect to? If you see any other variable, then that's where the chain rule is going to have to be applied. You can take the derivative like you know and love, but you always have to attach on this dy dx or some sort of notation to remind you that the chain rule has been applied. So we'll get back to this. We'll have a lot more explanation for the next example, but I want to kind of finish off this problem. If we were using implicit differentiation, and you notice the whole problem was for us to find dy dx, the derivative of y with respect to x. We now have an equation with dy dx in it. So the whole key to all of this would be for us to solve for dy dx, because that is what we wanted to find. So a little bit of algebra. That's the key to calculus. What I would probably do is I keep the dy dx where it's located and subtract the 2x from both sides. And then if I was going to solve for dy dx, it's some sort of expression, kind of keeping in mind that you're multiplying the 8y by it. Dividing both sides by 8y, you're going to get dy dx. Negative 2x over 8y. You want to be a little prettier and reduce your fraction? Yes, we always do when possible. We do have some liberties here because we're elite calculus students. Sometimes it's not as important, but sometimes it does simplify the problem a little bit. So at this stage, right here, if I can label this, this is the derivative as a function of not just x, but it's a function of x and y. And that is taken, oops, sorry about that. That is taken from the implicit form. So when we're finished, we end up having a function of two different variables. But the question would be, if we were taking the derivative of the same equation, you know, x squared plus 4y squared equals 5 down here and then up here, shouldn't we get the same answers? And so that's kind of where I want to explore a little bit. I'm going to need a little scratch paper here. So I'm going to scoot off a little to the right, as I have been. So maybe you guys need to attach another paper. But the question is, maybe I should keep it on the lines. is derivative of y with respect to x, which is equal to negative x over 4y from our implicit differentiation, is it the same as what we got from our process above? So I think it was x over 2 times square root of 5 minus x squared. So we want to double check and we want to verify. And it's kind of a way to check if you're able to do so. I just want to make sure we have a function of x and y right here. Function of x and y. And here it's just a pure function of x. So the key is looking at who is y? Who was y to begin with? And so you could take your particular equation, and we already solved it for y. It was solved for y up here. So I'll write it out for you just in case. We can't see it sometimes. So my y was actually equal to, I think I kind of made it a little bit different. We can play with it. I'll say it's plus or minus 1/2 times the square root of 5 minus x squared. That's what y was supposed to be. So if I were to replace that y with this expression, let's see. Okay, so if that's the case, I'm just kind of working vertically. Dy dx, I saw negative x over 4, and then I'm pretty much multiplying that by my plus or minus 1/2 times square root of 5 minus x squared. I'll lengthen that fraction bar. Let's play. Well, 4 times 1/2 gives us 2, so we no longer have a complex fraction. So I can rewrite it. I have negative x over plus or minus 2 square root of 5 minus x squared. And then you kind of notice if you have a negative sign divided by a plus and negative sign, what it does is it reverses the direction of the plus and minus. So the minus would be on top, the plus would be on the bottom. So what would happen, no matter what, you end up getting a positive and a negative case. And so you would still see x over 2 over 5 minus x squared. And so what's our question? If we're comparing this to what we got. And yeah, it is the same. So that's pretty cool in terms of a nice little trick to help us out. It actually helped us avoid some of the radical notation. We had to kind of play with it at the end if we wanted everything in terms of x, but I mean, it gives us a nice little technique to kind of help us out. So I do want to play around a little bit and show a few more examples. And I also want to kind of give you, I should leave that there for a second. I'd like to give you an alternative, the dy dx notation that we've been using. It's very nice, but sometimes it gets a little bit tedious. There's a lot of writing going on when we're going through this. So one of the conventions that we use is we like to replace the dy dx notation, just so that you kind of say, we go with one of the other versions. Instead of saying derivative of y with respect to x, a lot of times we end up using this y prime notation because it makes the math look a little bit more streamlined. So we don't see so many dy dx's everywhere. And you're allowed to use this, but you want to make sure you're always keeping track of what variable you're taking the derivative with respect to. You can't just throw y primes in there. Sometimes things change up a bit. So sometimes you may use an x prime depending on what that derivative with respect to what variable it's. I tend to love what is it, the Leibniz notation. I love this for section 2.8 when we start dealing with related rates. It really gives us a heads up of how to set up our problem. But a lot of times when I'm using implicit differentiation, I tend to use this y prime part a little bit more. So I'll kind of show you with part A and part B so you can see the difference for yourself. And it's kind of a matter of preference. So example 2, you'll notice that I have part A and part B looking almost exactly the same. But you want to pay attention to what variable are we taking the derivative with respect to? And so this is where I'm kind of noticing, part A is asking you to take the derivative with respect to x. And part B is asking you to take the derivative with respect to y. So we have to be really careful with our notation. And this is where kind of starting off with understanding dy dx or dx dy will help us with understanding, do we use y prime or do we use x prime? So I'll write it both ways so that you can kind of make that decision for yourself. So part A, if I want to take the derivative with respect to x, it's the derivative of a sum. So I can take the derivative of each individual term. As long as I'm taking the derivative with respect to x, anyone that has just a pure function of x, you take the derivative like you know and love. So derivative of 3x squared is 6x. Let's make that 6 a little prettier. Here we go. And then now you'll notice, and that's kind of where the caution kind of comes into play, I see that I'm taking the derivative of sine of y. Remember, y is a function of x. So I can take the derivative of sine like I know and love. Derivative of sine of something is cosine of something, but it's the cosine of y. But I have to apply my chain rule. So I'd be multiplying the cosine of y by the derivative of y with respect to x. Remember those denominator, I guess you call it denominator notation? They should match up. We shouldn't be changing it around. Now, if you prefer to kind of, sometimes you're using implicit differentiation for something else, you could rewrite it so that it's cosine y, as long as you understand that dy dx is y prime. So at this point, this is all we can do to find the derivative. They didn't really tell us who y is. I believe part A, technically you could explicitly solve it for y. It seems like it's separable, so we can play with it. But right now, I just wanted to make this point. And the point is, you ask yourself, with respect to what variable? This is why people talk to themselves. You see mathematicians talk to themselves all the time because they've got to ask themselves questions before they proceed with the problem. So kind of showing you the difference between part A and part B, we'll get slightly different answers because we're taking the derivative with respect to a different variable. So here, if you notice, I'll do this in green. Part B, still the same idea. Derivative of a sum is the sum of the separate derivatives. But your issue when you take the derivative of the 3x squared, we have to pay attention is that this variable is an x. So yes, you can take the derivative like you know and love. What is that? Derivative of 3x squared, yes, it's 6x. But we have to apply the chain rule because x is a function of y. So we have dx times dy, or dx over dy. Now, if you take the derivative of sine of y, that's the variable they're caring about. So you can take the derivative as normal. Derivative of sine is cosine of y. And what happens? I want to clean this up a little bit if you were interested. Dx dy is considered x prime. Not x to the x, excuse me. Let's make that prime a little bit more. And so you can kind of see the difference between trying to take a derivative with respect to x versus a derivative with respect to y. And this sort of idea, it actually is preparing you for section 2.8. A lot of times everything's not in terms of x and y, so we have to really be careful about what are we supposed to calculate the rate of change with? What's happening there? So you practice. So we're trying to get good. I'm going to look at part C and just kind of pay attention to, it gives us a derivative with respect to x. So I kind of notice when I'm looking at my function itself, it's tangent of y squared plus x. So that's kind of a composition of a few different functions. And so the first thing you have to understand is we're saying, what is the derivative of tangent? So the derivative of tangent of something is secant squared of something. So that's the first thing we're going to write. So secant squared of something. And that something happened to be y squared plus x. But I know since I have more complication in my tangent argument, I'm looking at the derivative of the inside. We're going to write that in this one. So we have to add on a link to our chain for the chain rule. So now if we're looking at the derivative of the inside is y squared plus x. So if we're taking the derivative of the inside, we just have to keep track of things. Derivative of y squared, that's different than the specified derivative with respect to x. So this is where we're saying, okay, we could still take the derivative like normal. That's 2y, but we have to attach on a dy dx to account for that extra chain rule. There's a link within a link. Now, if you're taking the derivative of x, that's nice because it's just like normal. Derivative of x is 1x. So if you were interested, and maybe you have to use this for something else, you may see this written as, secant square of y squared plus x. And maybe instead of the notation dy dx, and maybe you may even see kind of being real careful so that you don't get confused with the argument versus what you're supposed to multiply it by. I don't think I need an extra bracket. You may see this rewritten as dy dx is the same as y prime. Still have this plus 1 going on though. So that's some sort of implicit differentiation. Just being real careful about what's happening with the variable. And a couple more examples to just kind of exercise our calculus muscles. Example 3, we'll play around with this, and then we'll also go and do example 4 so that you're really taking care of, what am I taking the derivative with respect to? So I want to kind of first look at the notation and notice, whoops, we just kind of went back. It's because I'm left-handed. Sometimes it messes up the screen. We are in section 2.6, I believe. There we go. So the first thing I look for is the notation. And I point to understanding, and maybe I even say this out loud to myself or I write it down on paper. Hey, Laura, we need to take the derivative with respect to x. So keep that in mind. The other thing I have to look for in this particular expression, I need to take the derivative of this. I also have an issue that not only am I taking the derivative, I have to go with the fact that I'm seeing a function of x times another function of x. And whenever you see that, that's where the product rule comes into play. So don't forget, that's going to imply that we have to use the product rule. And if you know you have to use the product rule, then we're going to run into some issues if we don't remember what it is. So sometimes if you already know you have to use the product rule, you might want to write really quick. The derivative of a product is the derivative of the second function, the second function times the derivative of the first function plus the first function times the derivative of the second function, or however way you like to remember it. And if I remember correctly, it kind of works like a, I'll just kind of keep this. I'll let you guys figure out what works best for you. So I want to point out that, just the presence of having an x as your factor on the outside, that's where the function's coming from. And then the cosine of 3y is g. The issue is kind of making sure, note, 5x squared times cosine of 3y is different than 5 times cosine of 3y. In our problem, this is our function times our function, but every once in a while, if we're looking at this, if we're understanding it this would be a constant times a function. So you really want to inspect this as you're going through this. Sometimes they, just the presence of having an x in that first part, the first factor, that's where we're having to understand, that's where we're using the product rule. So if that is the case, it is very good to try to keep the notation, maybe kind of have a list of organized scratch work, reminding yourself that f is 5x squared, it's always the first function. G is cosine of 3y. And then calculating the individual derivatives. So remember, it's with respect to x. So if we don't remember that, it's not going to be correct. So if I were to take the derivative of the first function, it's already in terms of x. It's the derivative as I know and love, not 10x squared, 10x. But if I'm going to take the derivative of the second function, this is where I have the issue. Because I have a y in it, I'm going to have to attach on a y prime somewhere in there. So rule of thumb, take the derivative as you know and love, pretending that you didn't know anything about implicit differentiation. So the derivative of cosine is negative sine of 3y. But because we are looking at the fact that we have an argument, I'm running out of colors, but we have it inside. We are multiplying it by the derivative of 3y. So that's the extra chain link. So that's 3. But also because it's y, you're saying the derivative of y. And so derivative of y is y prime. So that's where there's a few extra links, although it doesn't seem like it. It's because they wanted the derivative with respect to x. So we have a function within a function. Y is a function of x. Now, sometimes it helps for you to clean things up because if you're going to have to plug this in later, it could save you some cases of these minor mistakes. So a lot of times I'll kind of write the the trig function as the final factor, kind of switch the order. And kind of wanted to keep this consistent. I'm going to move this over just a little bit, just so I have enough room. And I can use my product rule to directly plug in these problems. Maybe using up a lot of space horizontally, so kind of keep that in mind as we're going. So I'm going to look at plugging in who g is. So in this case, g is cosine of 3y. I'm going to look at plugging in who is the derivative of f, which is 10x. The plus sign comes from the formula. I look at plugging in who the function f is, and it was 5x squared. I was going to color code that. Here we go. 5x squared. And that is multiplied by the derivative of the second function. So that's where we see the negative 3y prime times sine of 3y. And then we do have two separate terms. So, you know, it's nice to see if you can clean it up just a little bit. People like to write the monomial factor first and then the trig factor. And maybe simplify a little bit. The 5 times negative 3, change my mind, I have an eraser. I know that's negative. So I have negative 15x squared. Then you could put the y prime anywhere you like. And actually, it really doesn't matter to me. Sometimes people like to see it at the edge, but we'll work with it. You'll have your final answer. Everything gets multiplied, just kind of keep that in mind. Or if you are interested, because maybe you're trying to really interpret what's going on, this y prime part turns into dy dx. Kind of depends on what you're using this for later. So either version would be correct. Having fun yet? It is a lot of bookkeeping. Some of you are really happy with the last few sections because it's more of a computational step-by-step process. But the other half of you prefer to look things at visual as analytic geometry. So sometimes it's frustrating. So I can't make everyone happy no matter what we do. But practicing what you're a little bit weaker at always makes you better. So keep that in mind. We're going to play a little bit. So same expression we're taking the derivative of. I just want to point out, looking at with respect to what, this is what you maybe write yourself a note or note it off to the side. We are taking with respect to y this time. So always kind of be careful. And again, we have a function multiplied by another function. So this is the product rule once again. So we could kind of go with what that means. You could write out, if you're interested in your gf prime plus fg prime, maybe leaving yourself a lot of space because we're going to plug in a lot of things. And note taking or bookkeeping, a little bit of accounting, we say. So if f is 5x squared, it is different than what we're taking the derivative with respect to. So if we calculate the derivative of f, take it like normal, that's 10x, but you still have to attach on a y prime. Excuse me. What was I taking with respect to? Y, I have to attach on an x prime. And again, if that's bothering you, maybe a little side note, if you say dy dx, that's y prime. If you say dx with respect to y, that's x prime. Maybe that helps out a little bit. So those little clues we help ourselves out with. Okay, so just remember that it's multiplied. And I'll take it a little bit below. Sometimes I like them side by side, but if I'm color coding it, I can tell. I have G is the cosine of 3y. And we're good to go here. We don't have to worry about implicit differentiation chain. So we don't have to worry about attaching x primes, but we do have to worry about chain rule because it's a function of a function. So derivative of cosine is negative sine of something. But we have that extra chain link because the inside, the argument was more complicated than just a y. So if we want to clean this up just a little bit, I should have negative 3 sine of 3y. So those are our functions to now plug in. So I'll be looking at plugging in G. So when I do that, it's cosine of 3y. That's going to get multiplied by the derivative of f. So that is 10 times x prime. If you'd like to highlight your primes in different colors, sometimes that helps so we don't get confused. Depends on how happy you are with all this bookkeeping. It's really easy to make a mistake. And they always say the difference between an A minus and a B plus in calculus is just a negative sign. Well, in that case, it kind of is true, but it really means the process. All the little mistakes you make, they add up. So be careful. And you know, again, if you're just taking it slow, don't rush through it, you're going to be fine. Let's finish this off. We have f times g prime. So the f was the 5x squared. And the g prime, I had times negative 3 sine of 3y. So again, if it's helpful, we could clean this up. And sometimes, again, I end up marking my x primes or y primes differently, so I keep track of them just in case I have to use them later. So you could clean this up a bit if you'd like. Again, putting the 10x with an x prime times cosine of 3y. And if you'd like, highlight that or something. And then making this a little bit different, we would have negative, this time 3 times 5. I'm freaking out. Did I multiply that right last time? Yeah, I did. Yeah, sometimes it's the stuff that we know already that gives us an issue, like multiplication. So 5 times negative 3 is negative 15, but you have the x squared. And then now we're just attaching on the sine of 3y. And excuse me, I should have put that in parentheses. What am I thinking? So this would be a perfectly fine representation of your answer. If you decided that you wanted to rewrite the x prime as this is dx dy, maybe that's preferable later on if you're maybe applying this calculation to something else. But it shouldn't matter at this point. So either one is correct. Hope you're getting some good practice here. So, you know, once you learn how to take the derivative or a new method to take a derivative, the next famous problem that comes into mind, if you have a function and you want to find the equation of the tangent line. So this concept never changes the whole way through all of your calculus courses. The only thing that changes is the type of function you're ending up taking the derivative of. So I hope that kind of sticks with you the entire way through your calculus series. It's always the issue of, in order for us to find an equation of a line, we need a slope and a point that it goes through. And how we calculate the slope in calculus is usually having to do with the derivative. So we're just going to apply this to our next thing. If we're looking at example 5, find the equation of the tangent line to really complicated equation. In fact, if I look at it, and I even if I tried really hard, this is impossible to solve for y, by the way. So this would be the case that you'd have to use implicit differentiation. You'd be stuck. That's why we teach you this technique, because it's going to be impossible. We can't solve this for y no matter what we do. So we'll get there. That's kind of where the major complication comes from, just finding the derivative. But we have to remember we're finding the derivative at the point 0, 1/2, and just kind of do some bookkeeping and kind of keep in mind, what does that mean? The x value is 0, the y value is 1/2. So we probably, what that usually means when we see dependent versus independent variable, it means that we're actually finding dy dx, derivative of y with respect to x or y prime. So kind of be careful so that you understand. And most of the time you are taking with respect to x, but every now and then they like to switch things up on you, so just be mindful. So again, if it's impossible to solve for y, what we need to do is use implicit differentiation. So if we do that, I'm looking at the left side of the equation, which is x squared plus y squared, and then there's the right side of the equation. So what I want to do is, okay, derivative of x squared is 2x. I'm going to kind of move things over to the left to give ourselves more room. There's a plus sign that's already there. Derivative of y squared is 2y, but we have to attach on the y prime because y is a function of x. There's that chain rule coming back. So left side derivative taken care of. Now right side derivative. What I'm seeing, I am seeing a composition of two functions, or it's a little more than one function, but I'm looking at something to the power of 2. So if I'm going to take the derivative of the right side, I'm going to say, okay, derivative of something squared is 2 times something. Then you kind of take off the power, 2 minus 1. Recopy that something. So I believe that's 2x squared plus 2y squared minus x. But we have to attach on the chain. So the derivative of the inside. I'll leave a little more room. It might take a little space. So then we go through the inside and say, okay, what is the derivative of 2x squared? Derivative of 2x squared is 4x. It was only in terms of x. We don't have to attach on anything special. Derivative of 2y squared. Take the derivative as usual, but it's a function of y. Y is a function of x. So yes, it's 4y, but we have to attach on the y prime. And a little more with the chain. Derivative of negative x is -1. So there's that extra part. Maybe I'll get rid of the underline just so that it doesn't complicate the expression that much. Now, you can go through this. I mean, sometimes they're really excited if you end up finding whoever y prime really is. You find the y prime as a function of x and y. But remember what you're trying to do later. And I know we kind of addressed this earlier, is sometimes you don't want to get tied up in the algebra if all you have to do is plug in a point. So sometimes, solving for y prime might not even be worth our time. So that's kind of my thought. I only care about y prime, or dy dx, at the point 0, 1/2. So don't bother solving for y prime here. I think it's going to cause more issues, but I mean, you don't always have to take my advice. I just have done this a lot, so I kind of see what ends up happening. The more complicated we make it, the more likely we make a mistake. So what I want to kind of make sure about is I'm only caring about what's happening at 0, 1/2. I'm going to go through and just plug in zeros and 1/2s everywhere. That might simplify the algebra a bit. First, it looks a little ugly, but we'll go with it. So let's recopy. Remember, they are referring to the x is 0, the y is 1/2. So if we're kind of going through this, we can just do a little bit of bookkeeping. So I'm going to look at 2. Now 2 times 0, then I have the plus, and this is where I have to be patient. So 2 times y is 1/2. If it will let me write, there we go. Here we go. So 2 times 1/2, but I still had that y prime on there, so I'm going to leave that. And usually I like to write it in a different color, so I'm aware it's there. So that's the left side of our formula. Right side of the formula, a little more exciting. We have a 2 that's already there. And since I'm plugging in a lot of values, this is where I'm going to start with the brackets. I'm going to kind of figure out, I'm taking kind of the skeleton of what I'm supposed to plug in, at least the first part. And here's the second part. Sometimes this sets me up, keeping in mind that kind of helps me understand that I don't want to get too caught up on everything. So all these parentheses are where either an x or y goes, and then we just be really careful. So x is, in our case, it's 0. So we can go where we find the x is 0. The y is 1/2. Minus an x, and again is 0. X again is 0. 4 times x. 4 times y prime is 4 times 1/2. And then we didn't have to plug anything at the end. So it could make our lives a little easier. I know it looks a little ugly right now, and I know a lot of you are really, really good at mental math. But when you go through these problems, if you make one little mistake, it throws the entire problem off and it gets quite frustrating. I strongly recommend just showing this. I know you guys think that's baby steps, but it really does help. It helps with those minor mistakes. So at this point, all we're doing now is just kind of cleaning it up. 2 times 0 is 0. You'll notice that when we multiply 2 by 1/2, we divide out the 2's, so we actually have left-hand side, y prime. And then just be patient. I'll leave the 2 intact, but then I'll kind of go through the terms and see what do I really need. I noticed that 2 times 0 squared is going to go out to 0. We don't have to worry about that. We don't see a 0. It's already there. So really what you have is 2 times 1/2 square. And if that helps you, that's 2 times 1/4. And I'm just noticing. I should have made it a parenthesis, but no, don't worry about that. But we do know that that's going to get multiplied by whatever we have. We have 4 times 0. Don't have to worry about that. 4 times 1/2 times y prime. The 2 goes into 4 twice. So we should get 2. And I'll just write the y prime in red just to make sure. 2 times y prime. And then we have the -1. You clean it up just a little bit more. It's going to end up where we see, and I'm just keeping the y primes in red so they stick out. 2 times 2 is 4. 4 divided by 4. Oh yeah, that's all a 1. Everything divides out. So we actually get y prime equals 2 times y prime minus 1. I'll take some time on that. And if you're going to solve for y prime, here it's a little nicer, less x's and y's everywhere. what do we subtract 2y prime from both sides? So that's going to give us negative y prime, y minus 2y prime, or y prime minus 2y prime. We get tongue-tied a lot too here. So if that happens, I get negative y prime equals -1. And if you're solving for y prime, divide both sides by -1, we finally get y prime equals just a 1. Ooh. So what does that mean? Like after all this work, we actually just calculated that the slope is equal to 1. So it kind of benefits us to kind of pay attention to the context of the problem. And sometimes, instead of trying to solve for y prime when we're in the generic form up here, just maybe plugging in your point could save you a little bit of time. But I'm so excited, but I always have to remember, am I done? Did it ask me to find the slope of the tangent line, or did it ask me to find the equation of the tangent line? And it is the equation. So remember, we just go a little bit off. If we're going to finish off the problem and talk about the equation of the tangent line, we could go through our point slope form. Remember, slope is 1, and then we're going through 0, 1/2. I'll double check. Yes. And so what that means is we can use point slope form, y minus 1/2 equals slope times x minus 0. Cleaned it up just a little bit because people love that slope intercept form. And we actually get y equals x plus 1/2. That is the equation of the tangent line at that point. Ooh, having fun yet? Sometimes once you kind of work out the kinks, these end up, maybe I'm sounding horrible right now, but it ends up being kind of fun, a little puzzle to solve. Maybe you don't think so yet, but you will. You practice, you get better. What do you think, Leica? Yeah? Okay. She says do one more example, so I'll do that. And here I'm going to introduce another concept to you, but after you've gone through implicit differentiation, this is not going to be too much of a stretch. We'll approach this a little bit later, but notice this is not a mistake. Y with quotation marks, it's not really quotation. This is actually known as not the first derivative, but the second derivative. But I should spell derivative correctly. So if you see y prime, that's the first derivative. If you see y double prime, that's the second derivative. You're probably wondering, will I ever see a y triple prime? Maybe. We'll have to see as we go. But now we see, for example 6, we're going to look at using, they are clear. They want us to use implicit differentiation. So they're making us employ this method to find the second derivative if we have x cubed plus y cubed equal 1. And there's a simplify completely as well. I'm really excited for us to see this. So if I'm going through this, it doesn't look too threatening at this point. I'm happy it's a little smaller. Maybe sometimes in my notes, I'm going to calculate the first derivative. And if we're doing this, we're probably taking the derivative of y with respect to x. Yeah, that's y double prime. So it could be useful for you to kind of keep that notation. Derivative of y with respect to x, but you're actually taking the derivative of the left side with respect to x is equal to the derivative of the right side with respect to x. So sometimes it's nice to kind of notate along the way what you're doing. Not only does it help me read it, it helps you understand later when you go back and review your notes if you're in calculus 2. Or even next week, we'll say. So if I'm finding the derivative with respect to x, I'm going to go through this process one more time. We take our time on this. Derivative of x cubed. With respect to x, we're in good shape. That's just going to be 3 times x squared. Derivative of y cubed, that's where we run into the chain rule. Derivative of y cubed is 3y squared, but you have to attach on a y prime. Y is a function of x, the chain rule comes into play. Good news though, derivative of a constant, no matter what you take the variable with respect to, it's 0. So that's not so bad. Now, there's more than one way to do this. I just want to take you through the exercise. So I'm really working out your muscles on this one. You can see if you can solve it for y prime and then try to take the derivative that way. We can play with that, but I really want to go through the idea of using implicit differentiation just to get you to exercise this. There'll be some cases in calculus along the way that you have no choices. So let's practice a little bit rougher. More than one way to go. Or maybe it's not so rough, we'll see. I think if we were trying to do, yeah, maybe if you were to solve for y prime, you'd end up getting a quotient, and usually people, if they have a choice, they rather use the product rule than the quotient rule, so maybe you can explore, see what works better for you. But I'd rather use implicit differentiation. So one more time, and I'm taking just my time on this, I'm taking the derivative of each side with respect to x. And so if I'm kind of looking at what I see already, 3x squared plus 3y squared times y prime and 0. You know, you can skip steps here and there, but it's always nice for formal notes. You can go back and rewind and find out, how did I get that step? Well, let's go through this. So we have the derivative of a sum, and let me make sure, I like to mark where my primes are just so I don't lose it along the way. It's so easy to skip over it. So we're going to go through derivative of 3x squared with respect to x. We calculate this. This is a very nice, it's a 6x. We're going to have to be super careful right here. It is trickier than we think it is. This is a product. This is a product of two functions of y, which y is a function of x. So here we go. We're going to have to use the product rule. And I don't know if it's beneficial to use it within the problem or write the work off to the side. I kind of think since I already don't have any complications on the right side and there's no more terms in the problem, you'll probably see me work it out within the context of the problem. But if you prefer, you can do the product rule off to the side and then plug it back in after. So whatever works for you. If I'm going to label this, it looks a little bit strange, but kind of keep in mind I had a plus sign at the beginning, so I'm not going to change that up. I'll just go with it this way. We're going to call this part F and G. So I'm trying to think of my color codes, but maybe I'll stay consistent with what I've been doing earlier. I have F in blue and G in green. So if I was using the product rule, I have G times F prime plus F times G prime. And might as well on the right-hand side just remind ourselves that we don't have to do anything. It's already 0. Derivative of 0 is still 0. Now I know this isn't standard notation to throw within the context of your problem, but it does help you keep everything in line. If you want to, on the side, a little accounting here, we have F equals 3y squared. So F prime is going to be Derivative of 3y squared is 6y, but we have to remember that we are attaching on the y prime. Y is a function of x. We could also talk about g. It's y prime. Now, if you're taking the derivative of a derivative, that is you taking the second derivative. So that's where that double prime goes. So now if we plug everything back in according to our bookkeeping, I still have 6x, nothing has changed there. But when I use g, I don't know if I'll use, I'll use the actual colors that I set up. So g is y prime. My f prime, according to my product rule, is 6y times y prime. So gf prime plus my f, I was going to use purple. Here we go. My f is equal to 3y squared. And my g prime, that is finally where I get the y prime prime, or second derivative y double prime, still equals 0. Now, if it is to your benefit, I mean, you can play around with this. You may kind of think about if you were trying to find the second derivative, we're not just highlighting the y prime, we are actually kind of looking at everywhere we see the y double prime, derivative of y with respect to x. But that's the second derivative. We'll talk about notation when we come up with that later. But if I'm going through this, and I'm going through this correctly, if I want to find the second derivative, y prime prime, I'll take this equation and I'll use algebra to solve it for y double prime. So the best way I know how, I like to leave y double prime where it's at. But it looks easier to move it over. We'll play around. I think it's easier to move one term over than it is to move both terms over. So let me rewrite this. I'm going to see this as 6x plus y prime times 6y prime y, or times 6. How do I want to do this? I'll just leave them out. I know there's a little prettier ways to write this, but I don't want to lose the idea. So y times 6y y prime. So we'll write this down. 6y, another y prime. So I'm really exaggerating my primes too, by the way, so be careful. I like to not lose them, so this is what I do. So 6x times y prime, 6y prime. Cool. Now, I still have the plus sign. Come on. It's getting tired itself. There we go. I want to move over this 3y squared y double prime. So when I do that, I'm subtracting it from both sides. I should have a negative, and that gives me 3y squared y double prime. And I'm reminding myself that this is what I have to solve for at the end, so might as well write it in red to remind myself. Now, if you'd like to clean this up just a little bit, some people like to put, if you're multiplying the same type of factor together, you can use exponents if you'd like, but sometimes all I just like to do is just kind of rearrange it so I can see that, oh yeah, it's y times y prime times y prime. Negative 3y squared times y double prime. And so sometimes we'll see this. I'm going to keep this in mind. Remember, we're solving for y double prime. So what do? Divide both sides by 3y squared. So if we do that, and I should be clear about this, I will. I'll show it just so that we don't miss that negative sign. So now what I see on the right-hand side, I have isolated the second derivative. And on the left-hand side, I have an expression. I have 6x plus 6y, y prime times y prime, over negative 3y squared. So I'm feeling pretty good, but if I'm looking at my first derivative and I notice it's in terms of a second derivative and it's in terms of y, if I already know what the first derivative is, I can actually start plugging that in. So maybe we should do that. We want to simplify it. Sometimes we think we're done and like we check our answer in the back of the book or website and it doesn't compute. It's usually because they want you to clean it up a little bit. So what I would notice, if I can, let's go back and look at maybe substituting in. Yes, like we do have to substitute it in. So we have to substitute in y prime. So this is kind of where I would kind of say, hey, let's go back and look at our previous work. Remember, we calculated the first derivative, or implicit differentiation. We already had an expression, 3x squared plus 3y squared times y prime equals 0. Noticing it's kind of, you can explicitly solve, excuse me, it's getting late, getting tongue-tied. You actually could solve for y prime. So if you were to move subtract 3x squared from both sides, you would have 3y squared with a y prime. And then if you divide both sides, I'll go in blue just in case, divide both sides by 3y squared, 3y squared. What do we get? Y prime all by itself. It's getting so exciting. So y prime all by itself, and if we clean it up a little bit, we should get negative x squared over y squared. So if you go and replace that back in, let's see. Take a little time. Okay, so if we have that, let's go through. I'm going to go back to my expression. I still have the 6x plus 6y. And I'll multiply those back in. So let me substitute these in. Instead of y prime, we are going to take this root. So that's negative x squared over y squared times negative x squared over y squared. And just kind of keeping that in mind, I just replaced the y prime with its function in terms of x and y. And I'll clean it up a bit. Don't forget there was a negative 3y squared on the denominator, and we have y double prime. If you'd like, keep color coding. So let's clean this up a bit. A little bit of fun. If we wanted to, I'm kind of seeing a 6x, 6y. I'll deal with that a little bit. I'd like to factor it out. That's what I'm thinking in my mind right now. But sometimes you see it at the beginning and sometimes you see it at the end. Let's go. We're just kind of cleaning this up. If I was multiplying negative times negative, I'm going to get a positive. So all I'm doing is simplifying the y prime part. This would leave me with x to the fourth over y to the fourth, still over negative 3y squared. Hang in there, everyone. I know it's a little tough at the end of the section. Lucky for you, you guys can pause and take a break and then come back to it if you're feeling super tired. But if you were in lecture class, you'd be stuck. So it's kind of nice. So we're cleaning this up. Now what I'm noticing about the numerator, taking a little more space here, I'm keeping the 6x. I'm going to notice I have a complex fraction in the issue here, but y over y to the fourth, that's going to leave us, we still have a 6, I'll keep that there, but that's going to leave us with x to the fourth over y cubed. So I'm feeling pretty good here. Little nicer. Still a complex fraction though. Negative 3y squared. Still, my friends, equaling the second derivative. I'm just excited to see where this takes me. We'll see. So this is kind of what I'm noticing here is I really see 6s, I see a 3. This might be a good opportunity for me to factor out a 6 from the numerator. Maybe saving myself a little bit of thoughts here. I have an x plus, and there's where I have that x to the fourth over y cubed. And that's all over still negative 3y squared. Still equals second derivative. Hang in there, we're almost there. And this is where I'm seeing, yeah, I'm allowed to cancel out factors. 6 over 3 gives me a 2. So I'm kind of not needing that negative 3 in the denominator anymore. So I'm going to clean this up just a little bit more. I have negative 2 times x plus x to the fourth over y cubed over y squared still equals the second derivative. And you're like, why are you doing this to me? I'm seeing something very interesting right here. It's going to happen soon. What I want to play with, I guess I could have taken an x out of there, but my issue is the complex fraction. I see this y cubed. I see there's something I want to deal with. I'd like to get rid of it, actually. So I play with my algebra from my past. Hang in there, everyone. If I take my complex fraction and I multiply it by y cubed over y cubed, I'm not changing the complex fraction because I'm multiplying by 1. But what I am doing is getting rid of that extra fraction in the numerator. So what this should give me, and I know there's more than one way to take this, we still see the negative 2 on the outside. Instead of us looking at just an x, this y cubed right here, kind of we can distribute in. So that's where we have it here. When we distribute the y cubed to this second term, this is where the magic happens. This allows us to divide out the y cubes in the numerator. So we are left with x to the fourth. So I'm cleaning it up just a little bit. However, I've made the denominator a little bit uglier. Don't worry about it, we'll get there. So y cubed times y squared gives us y to the fifth in the denominator, and we're still equal to the second derivative. Now, my idea is, maybe I don't want to see so much complication. Something that I am looking out for is the fact that they kind of gave me some sort of relationship between every time I saw x cubed and a y cubed, and I'm kind of seeing a y cubed. So I'm kind of wondering, in the original problem where they said x cubed plus y cubed equals 1, I can clean this up even further. And you may not see it at the moment, but Right now I'm looking at this x. If I were to factor that out, and maybe I should have done it earlier, but sometimes we don't know when we're starting. If I actually factor out that x, and I go through this, I'm going to get a y cubed plus an x cubed. Still all over y to the 5th. But that's equal to the second derivative. And now do you see where I'm headed? You can replace that y cubed plus x cubed with the number 1. Somehow I sense you're not as excited about this, but I think that's awesome. We just kind of simplified this down to a single term. All that complication. So let's do that. If I replace this with 1, my final way to go, I should be getting negative 2x over y to the 5th. And now we have the second derivative. And that is as simplified as we can make it. Wow. Yeah, we did a lot of work here. But I'd like to kind of point out, sometimes you all are headed in the right direction. And I don't want you to get too frustrated, because sometimes if you're looking at a solution manual or some sort of written out process, people will skip steps along the way and jump from something that we wouldn't have known, maybe somewhere at one of the top 3 steps. They automatically skip all these steps and then they jump down to the bottom, and you're like, well, how did I get that? Well, I wanted to go through an example with you to kind of justify. We are pulling a lot of algebra out from our past. So best thing you can do if you want to get better at these, even though some of them could be painful, is just keep practicing, keep redoing similar problems. Thank you for listening. I'll see you in the next section.